show a stunning drone view of a modern city and a big flyover with vehicles moving smoothly connected with more roadways through viaduct and ramp flyover with very scenic view. Have you ever wondered how modern flyovers are built? These towering structures handle massive of steel tendons inside the bridge structure. Inside this beautiful flyover, high-tension steel tendons are protected within conduits. But what if these tendons begin to corrode? After just a few months, this corrosion can weaken the structure, reducing its load-bearing capacity and leading to dangerous cracks or failures. But why does this happen? Stay traffic loads daily, but their strength comes from brilliant engineering. Today, we'll take a deep dive into the step-by-step process of flyover construction and uncover some surprising facts about their design. 1. The role of steel tendons in flyovers. Show an animation tuned to find out. 2. The engineering secret. Box girders. Show a time-lapse of box girder segments being placed. Would you believe that modern flyovers are built using hollow box girders? These structures might look simple, but they use a smart male-female interlocking system to connect multiple segments securely. Show an animation of inserting a steel tendon through the box girders. When these steel tendons are tightened, they enhance the load-bearing strength of the entire flyover. This technique, known as press dressing, helps the structure handle heavy traffic without cracking under pressure. 3. The star of the show, box girders. Show an inside look at the box girder fabrication process. Welcome to the box girder fabrication site. Engineers use hydraulic-powered formworks to shape the girders. Steel reinforcements are placed inside before pouring concrete. After curing, the inner and bottom formworks are removed, revealing the final box girder. Zoom in on the holes in the girder. But why do these girders have so many holes? Stay with us to find out. 4. Box girder assembly, the precision fit. Show workers applying epoxy and assembling box girders. Before connecting the box girders, workers apply a special epoxy resin to the girder faces. This allows for a perfect male-female interlock, ensuring a snug and secure connection. But wait! Did you notice the small gap left between segments? This isn't a mistake, it's deliberate engineering. If the girders were assembled perfectly without a gap, there would be no way to fit the final girder into place. Solution: engineers fill this gap with reinforcement bars and concrete, creating a seamless, rock-solid structure. 5. How a flyover transfers weight. Show a flyover with arrows depicting weight distribution. So, how does a flyover actually transfer weight? Let's break it down step by step. 1. The superstructure, including vehicles and the bridge deck, transfers weight to the bridge bearings. 2. The bridge bearings pass the load to the piers. 3. The piers send the load to the pile cap. Finally, the pile cap distributes the weight into deep piles, which are anchored in hard strata below the ground. Show an animation of engineers drilling into the ground. Engineers search for a strong hard strata layer deep underground. This ensures that the entire flyover remains super stable. But what happens if the piles don't reach the hard strata? The flyover could become unstable, leading to potential collapse. This is why deep foundations are crucial. 6. The construction process. Show time-lapse footage of workers constructing the foundation. Step 1. Digging deep for the piles. Engineers drill deep into the ground, searching for the hard strata. Once found, they insert reinforcement bars and pour concrete. After a 14-day curing period, the pile foundation is ready to bear tremendous loads. Step 2. Constructing the piers. All piles are connected using a solid pile cap. Next, piers are built, topped with beautifully curved pier canopies. To pour concrete at such heights, powerful concrete pumps are used. 7. Strengthening flyovers with minimal materials. Show a real-life hydraulic jack stretching multiple tendons at once. In real-world construction, hydraulic jacks are capable of stretching dozens of tendons simultaneously. Initially, we planned to demonstrate a 3-cable stretch using our 3D printed model. However, due to load limitations in our plastic parts, we had to settle for a single cable demonstration. Despite using just a few high-tension steel cables, the strength of a flyover increases exponentially. This is why post-stressed bridges can support massive loads while maintaining structural integrity. Opto 8. The role of abutments in flyovers. Show an animation of an abutment connecting the ground to the flyover. The structure connecting the ground to the flyover deck is called an abutment. Its angle and design are crucial for ensuring a smooth transition for vehicles moving onto the flyover. The area behind the abutments is filled with soil to provide stability and prevent sudden drops. Once the abutments are in place, vehicles can now smoothly glide onto the flyover, experiencing a seamless ride. 9. The power of the launching gantry. Show a huge segmental launching gantry lifting girders. The segmental launching gantry LG is the largest machine in the entire project. It's almost like a robot with 4 legs, assembling the bridge piece by piece. Here's how it works. The gantry lifts and positions each box girder precisely. It moves forward to the next section using its 4 adjustable legs. Once one section is complete, it advances to the next, ensuring perfect alignment. 10. The launching gantry moves forward. Show an animation of the launching gantry moving to the next pier. Now that the current segment is assembled, it's time for the launching gantry LG to move forward. 1. The front leg of the gantry is supported on the next pier cap. 2. The rear middle leg moves forward and rests at the front of the deck. 3. The support bracket shifts forward to the next pier, ensuring stability. 4. Finally, the rear leg retracts and the entire gantry moves forward. If you observe the gantry's position now, it's identical to its position before assembling the previous segment. The main legs are centered, and the gantry is perfectly aligned, ready to start the next segment installation. This cycle is repeated until the entire flyover structure is completed. 11. The most crucial step, post-tensioning steel tendons. Show an animation of workers inserting steel tendon wires through the box girders. Now comes the most crucial operation, the insertion of super strong steel tendon wires through the box girders. These wires are tightened with extreme precision, ensuring that the assembled segments remain stable even without the support of the gantry crane. Did you know? At this stage, the flyover segment is already strong enough to carry the weight of at least 20 cars. But here's a big question. Are these steel tendons only meant to hold the girders together? Surprisingly, even without these tendons, the girders would initially remain stable. However, within a few months, cracks would start forming at the bottom of the girders, eventually leading to structural failure. 12. The power of post-stressing in flyovers. Show a demonstration of 2 concrete flyover models, one with post-stressing, one without. Welcome to the brilliant engineering of post-stressed concrete. Show an animation of 2 different flyovers being tested under load. In one girder, steel tendons are tightened under extreme tension. In another girder, the tendons are present but not under stress. Let's test their strength. 1. The non-stressed girder fails suddenly under weight. It snaps instantly. 2. The post-stressed girder holds much more weight before failing, and even then, the failure is gradual and controlled. This is the power of post-stressing. It enhances the bridge's load-carrying capacity, durability, and resistance to cracking. 13. Why does post-stressing make a flyover stronger? Show an animation of a flyover segment bending under load. When a bridge segment is supported at both ends, it naturally bends under load. The top portion of the segment experiences compression. The bottom portion experiences tension, making it prone to cracks. Here's the problem. Concrete is strong in compression, but weak in tension. This means the bottom part of the flyover is highly vulnerable to cracks. Solution: post-stressing by tightening steel tendons before the bridge is even operational. Engineers pre-compress the concrete to counteract future tensile stress. As a result, even under heavy traffic loads, the cracks never develop, ensuring the bridge lasts for decades without failure. Show a fully completed flyover with traffic flowing smoothly. Modern flyovers are a marvel of engineering. From deep foundations to the smart use of press-stressed box girders, every step ensures durability and strength. Now that you know how they're built, you'll never look at a flyover the same way again. Show a completed flyover with vehicles moving smoothly. Closing parenthesis. From deep foundations to high-tech post-stressing, modern flyovers are true engineering marvels. Every step in their construction ensures maximum strength, durability, and safety. If you enjoyed this deep dive into flyover construction, don't forget to like, share, and subscribe for more amazing engineering insights. Point 14. The science behind tensioning steel tendons. Show an animation of powerful hydraulic jacks tightening steel tendons inside the flyover. Ever wondered how engineers keep these steel tendons in high tension permanently? The process starts with powerful hydraulic jacks that handle the tough job of tensioning the cables. Step 1. A high-pressure fluid moves the piston, pulling the steel tendons and tightening them to the required force. Step 2. Once the desired tension is achieved, workers release the pressure, remove the jack, and cut off the extra cable. But here's a question. Why don't these high-tension cables contract back to their original length once the hydraulic jack is removed? Point 15. The secret. Clever wedge mechanism. Show a 3D animation or real-life footage of a wedge mechanism in action. To understand this, let's take a closer look at the brilliantly simple wedge system inside the post-tensioning mechanism. We 3D printed a simplified model to demonstrate exactly how this works. How do wedges keep the tendons in place? 1. These small but powerful wedges are designed to allow the cable to move outward when stretched. 2. However, once stretched, the wedges lock the cable in place, preventing it from moving back even if all external pressure is removed. Let's visualize two different situations. If the block surrounding the wedges moves, it tightens the wedges around the cable, locking it in place. But if someone tries to pull the cable outward, the wedges remain loose, allowing the tendon to stretch. Now, let's apply this to post-tensioning. As the hydraulic jack pulls the tendon, the outer wedges tighten, allowing the cable to move. But once the jack releases pressure, the inner wedges grip the cable tightly, preventing it from contracting. The result? The tendons remain permanently in tension, reinforcing the bridge structure for decades. This is the genius of post-tensioning, a simple yet incredibly effective engineering feat. 16. The genius behind interchange designs. Show an aerial view of a well-designed flyover interchange. Ever wondered how engineers come up with these intricate, multi-level interchange designs? The key to a well-planned flyover system is its ability to reduce traffic congestion, minimize land usage, and ensure smooth traffic flow. One of the most common interchange designs is the three-way interchange, used where one road terminates at another major road. Designed to allow smooth entry and exit without causing congestion, reduces land use, construction costs, and lane weaving. With advanced engineering and meticulous planning, these flyover interchanges ensure safe and efficient movement for millions every day. Underscore. A conclusion is here. Show an aerial shot of a completed flyover with cars moving seamlessly. From deep foundations and post-stress tendons to clever interchange designs, modern flyovers are a true testament to the brilliance of civil engineering. Did you enjoy this deep dive into flyover construction? Like, share, and subscribe for more fascinating insights into civil engineering. Point 17. The beauty of Cloverleaf and other interchange designs. Show an aerial view of a well-designed Cloverleaf interchange. At the ends of expressways or as transition points, a variety of interchange designs help ensure smooth traffic flow. Among them, the Cloverleaf interchange is often considered one of the most beautiful innovations in civil engineering. This design, resembling a four-leaf clover, is used where two highways intersect and allows for continuous movement without traffic signals. How does it work? Vehicles can transition to any direction without stopping thanks to carefully designed looping ramps. Watch this animation to see how smoothly the vehicles merge and exit without interruptions. However, there are challenges. The Cloverleaf design requires a lot of space and creates weaving issues as vehicles merge and exit within short distances. Underscore 18. The efficiency of diamond and partial Cloverleaf interchanges. Show a simple diamond interchange model. For locations with limited space, a diamond interchange is a great alternative. This design features for ramps arranged in a diamond shape, allowing for smooth transitions between a highway and a secondary road. Benefits: minimal land use, efficient for moderate traffic volumes. Direct access between roads. However, it has one limitation. The presence of traffic signals can cause delays during peak hours. A modification of the Cloverleaf, the partial Cloverleaf interchange, offers an improved solution. By removing some of the loops, this design reduces space requirements and minimizes weaving issues. It blends features from both Cloverleaf and diamond interchanges, making it particularly effective in suburban areas. 19. Bonded versus unbonded post-tensioning in bridges. Show a cutaway view of post-tensioned cables inside a flyover. Engineers have to major ways to handle post-tensioning cables inside flyovers. Bonded post-tensioning, unbonded post-tensioning. What's the difference? In bonded post-tensioning, the steel cables are grouted into place, creating a strong bond with the surrounding concrete. In unbonded post-tensioning, the cables remain inside a conduit, allowing them to move independently. Advantages and disadvantages. Bonded post-tensioning provides greater resistance to corrosion but requires more cables to achieve the same level of compression. Unbonded post-tensioning requires grease inside the conduit to prevent corrosion, but it provides more flexibility in tensioning operations. Both methods are used depending on the structural needs and environmental conditions. 20. Why do flyovers have expansion joints? Show an animation of a gap in a concrete structure expanding and contracting. Have you ever noticed gaps or strange patterns in flyovers? These are expansion joints, an essential feature of long concrete structures. Why do we need expansion joints? Materials like concrete expand and contract due to temperature changes. If a bridge was completely rigid, it would develop cracks over time. How do expansion joints work? A floating support member slides over bearings, allowing for smooth expansion and contraction. Rubber strips between lamella plates prevent gaps while absorbing movement. This ensures flyovers can handle extreme changes without cracking. Under 21. Concrete versus steel flyovers. Which is better? Show a comparison between concrete and steel flyovers. Most flyovers we see today are made of concrete, but some use steel girders. Why? Concrete flyovers. Most commonly used due to durability and cost-effectiveness. Stronger in compression, making it ideal for bridges with heavy loads. Longer construction period but lower maintenance costs. Steel flyovers, lighter and stronger compared to concrete. Faster to construct, making them ideal for urgent projects. Higher cost and requires more maintenance due to corrosion risk. Example: the flyover in San Antonio, Texas, is a great example of a steel flyover designed for quick assembly. 22. Key benefits of flyovers. 1. Reduce traffic congestion. Flyovers eliminate bottlenecks by allowing vehicles to bypass intersections without stopping. Interchanges like Cloverleaf and diamond designs enable smooth traffic flow, reducing travel time. 2. Enhanced road safety. By reducing intersections, flyovers significantly decrease the chances of collisions. Separated lanes and controlled entry-exit points minimize the risk of high-speed crashes. 3. Efficient land utilization. Designs such as the partial cloverleaf and diamond interchanges maximize land use while maintaining efficient traffic movement. 4. Increased load-bearing capacity. The use of post-tensioning cables strengthens concrete, allowing flyovers to withstand heavy traffic loads without cracking. This ensures long-term durability, reducing frequent maintenance needs. 5. Improved urban connectivity. Flyovers serve as essential links between highways, expressways, and city roads, reducing travel distance and fuel consumption. 6. Faster construction techniques. Steel flyovers, while costly, can be assembled quickly, making them ideal for urgent infrastructure projects. Launching gantry methods streamline construction by enabling the safe and efficient placement of large segments. 23. Safety measures in flyover construction and maintenance. Post-tensioning for structural integrity. By keeping steel tendons in tension, concrete flyovers are protected from cracks and failures, ensuring longevity. Bonded versus unbonded post-tensioning techniques are chosen based on the environmental and structural demands. Expansion joints for temperature adaptation. Flyovers experience expansion and contraction due to temperature changes. Expansion joints prevent cracking while ensuring a smooth ride for vehicles. Hydraulic jack precision and safety checks. Hydraulic jacks tension steel cables with high accuracy, preventing sudden structural failures. The use of engineered wedges ensures permanent tension even after the jacks are removed. Seismic and load testing. Flyovers undergo rigorous seismic tests to withstand earthquakes and extreme loads. Engineers conduct simulated load testing using weights equivalent to several heavy vehicles to ensure structural safety. Regular maintenance and corrosion protection. Unbonded tendons are coated with grease to prevent corrosion, extending the flyover's lifespan. Periodic inspections and reinforcements ensure safety, especially in high-traffic areas. Conclusion? The engineering marvel of flyovers. Benefits and safety. Flyovers and bridges represent some of the most remarkable achievements in civil engineering, seamlessly connecting cities, reducing traffic congestion, and enhancing transportation efficiency. The intricate processes involved in their construction, such as launching gantries, post-tensioning, and expansion joints, demonstrate the extraordinary precision and innovation required to build structures that withstand time, load, and environmental factors. From the use of box girders with post-tensioned cables to the strategic placement of expansion joints, every element in flyover construction plays a crucial role in ensuring stability and longevity. The careful selection between concrete and steel flyovers further highlights the engineering decisions made based on durability, construction speed, and cost-effectiveness. Each interchange design, whether a cloverleaf, diamond, or partial cloverleaf, is planned meticulously to optimize traffic flow, minimize land use, and reduce weaving issues. But beyond their structural complexity, flyovers provide significant benefits to urban mobility and safety. A special thanks and final thoughts. Flyovers are not just elevated roads, they are engineering marvels that transform urban landscapes. With advancements in post-tensioning, launching gantries, and interchange designs, civil engineers continue to build stronger, safer, and more efficient transportation networks. The combination of technology, innovation, and precise engineering ensures that these structures will remain reliable, durable, and safe for decades to come. As cities grow and traffic volumes increase, modern flyover designs will continue to evolve, integrating sustainable materials, intelligent traffic systems, and advanced construction techniques. By prioritizing safety and efficiency, civil engineers ensure that future transportation networks are both resilient and adaptive to urban demands. Thank you for exploring the world of flyover engineering with us. Stay curious, stay inspired, show a time-lapse of flyover construction from start to finish. We extend our gratitude to Bambula for providing technical support for this video. Their 3D printed models allowed us to demonstrate the post-tensioning process in detail. Want to explore the world of 3D printing? Check out their website for more exciting innovations. If you enjoyed this deep dive into civil engineering, make sure to like this video, subscribe to our channel Civil Engineering Edge. Stay tuned for more incredible engineering insights. Thank you for watching, take care, and see you in the next video.